So next topic is exponential and logarithmic functions. We start with the exponential function. Definition. Y equals a to the power of x with a positive does not equal 1 and x is a real number is called an exponential function with base a. So one might ask, why are we asking a to be not 1? If a is 1, then everything 1 to any power is 1. So if a is 1, then 1 to any power is 1. So we get horizontal line. If a is negative, then, for example, if a is negative 1 to the power x any 1/2 will be imaginary number. So we would like to avoid those complex numbers. So again, this is a definition of exponential function with base a, where the a is a base, x is exponent, a positive does not equal 1, and x any real number. So to avoid complex numbers, we're assuming a is greater than 0. To avoid trivial case, we're assuming a is not 1. Otherwise, 1 to any power is 1, you get horizontal. So let's list the properties of it. Domain of this function, all the real numbers. Any positive number can be raised to the real number exponent. The next, the range of it. Positive number to any exponent is still positive. And the graph goes, the graph of y equals a to the power x goes via, if x is 0, y is 1. So all of them, no matter what a, go through the point 0. So y equals 0 is a horizontal line. So the graph approaches horizontal line but never touches. It's always greater than 0. So y equals a to the power of x is increasing on negative infinity, infinity, if base is greater than 1. And y equals a to the power of x is decreasing function on its entire domain if a is between 0 and 1. Y equals a to the power of x is a 1-to-1 function on its entire domain. So let's see all this. On the graph. So here's the graph of the function y equals 2 to the power of x. See that green line? And this is y equals x, bisector of the third and the first quadrants. So y equals 2 to the power of x. As you see this, let me approach closer, closer, closer. See, it does not touch, but it looks like touching. It does not touch, okay, x-axis. So y equals 0 is the horizontal line. Y equals 0 is a horizontal asymptote. Okay. So here it is. Let's get the other one. Here it is. This is, the base is 1/2. So base A is between 0 and 1. The graph is decreasing. As you see this, when x moves from left to right, it's decreasing. Approaches x-axis. It does not touch. It looks like it's touching. It does not. Because domain is always positive real numbers. So here are both of them. So one is increasing. So when the base is greater than 1, it's increasing function. When the base is less than, between 0, it's decreasing function. So we're back now. Now we saw the function is one-to-one function. So we have the inverse. We have the inverse function. So the inverse exists. So what we can tell about the inverse? We're going just rewrite all those. You remember we did last time we did inverse function theory, so I can write this. So let's call the inverse. Let's find the inverse first. So inverse for y equals a to the power of x exists. Let's find out. So you take equation y equals a to the power of x, exchange x and y. You get x equals a to the power of y. Now solve for y. Unfortunately, let's call 1, 2. Unfortunately, equation 2 cannot be solved for y. That is why we make up a name for the solution of equation 2. So we're going to call it y equals logarithm x base a. So the solution of this equation we're going to call logarithm. So 3 means y equals logarithm x base a means a to the y equals x. This means 2, and vice versa. So from every exponential statement, we can move to logarithm. Let's do examples. Two to the second power equals 4. So that means 2 equals logarithm 4 base 2. 3 to the power of x equals 9. X equals logarithm 9 base 3. 10 to the second power equals 100. So 2 equals logarithm 100 base 10. 4 to the third power equals 64. That means 3 equals logarithm 64 base 4. So what's the logarithm means? The logarithm means to which power, this is a base, by the way. So in the notation, y equals logarithm x. X is called the base. This is a base. So simply it says, to which power this base has to raise to get 64? To which power I have to raise 4 to get 64? To the third power, 4 to the third, 64. To which power I have to raise 10 to get 100? To the second power, 10 to the second equals 100. To which power I have to raise 3 to get 9 to the power of x? Yeah, by the way, this is 2. To which power I have to raise 3 to get 9? 3 to the second, so x equals 2. So you just calculated logarithm. So what's the logarithm 9 base 3 means? It means 2. Why? Because 3 to the second is 9. 2 to the second is 4. So you start calculating logarithm, even though we made it that name. Let's try another one. What is the logarithm of 0.01 base 10? Simply, I'm asking to which power I have to raise 10 to get, you remember, what's the 0.01? It means 1 over 100. So to which power I have to raise 10 to get 1 over 100? To the negative 2. So we just calculate in logarithms. Logarithm 3 base 9. To which power I have to raise 9 to get 3? To the 1/2. Why? Because 9 to the 1/2 means square root of 9 means 3. Yeah, even though we made it up a name, now you can calculate logarithms. Again, logarithmic statement checked by the going to exponential. These two means the same thing. Now we know that we made it up a name, but we're comfortable. I guess we can play with this. Now we can get properties of it. So y equals logarithm x base a. So we have to invert everything, whatever we had for exponential, it's other way around. So number one, domain of the exponential becomes, range of exponential becomes domain of it. So domain of inverse equals positive real numbers. Range of this logarithmic function, this is inverse of f logarithmic s base a. So the range of it becomes domain of it. The graph of y equals a to the x goes through the 0, 1. So it's other way around. So I can write the graph of y equals logarithm x base a goes via 1, 0. We exchange x and y. So y equals 0 is a horizontal line. So x equals 0 is a vertical asymptote. I have to put asymptote here. It's a vertical asymptote. Sorry here, so I have to correct this. It's a horizontal asymptote. Horizontal line, but horizontal asymptote. So 5. So how it's going to 5 is going to look like for y equals the logarithm x base a is increasing on its domain. What's the domain of logarithm? 0, infinity. If a is greater than 1. I'm just rewriting this verbatim. And y equals logarithm x base a is decreasing on negative on its domain. Domain of logarithmic is 0, infinity. Domain 0, infinity. If a is between 0 and 1. And of course, number 6, y equals logarithm x base a is a 1-to-1 function on its domain. What's the domain? 0, infinity. Now we have a cycle properties. You remember we did this all. So let's write properties. Cycle. Or Back to the Future. So what was it first? So inverse of f of x was x for any x from the domain of x. Second one, f of the inverse of f of x was x for any x from the domain of the inverse. Let's write down those. My function is f of x is a to the power of x. So let's write it down. So inverse logarithm base a f of x a to the power of x equals x for any x from the domain of the original of the a to the power. The original of a to the power is all real numbers. The second one, a to the power logarithm x base a equals x for any x from the domain of logarithmic function 0, infinity. So those are properties. Those are cycle properties. The best way to memorize those one was using boxes. So here it is. I'm going to put this one. Logarithm box 1 to the box 2 base box 1 equals box 2. So box 2 can be any real number, the content. I can write this one using boxes. Box 1 to the power logarithm of box 2 base box 1. See, those two matching equals box 2. Where the box 2 is what? Any real number. So those are two important properties. Inside of the box, you can put anything as long as they satisfy this. Of course, box 1 is the base, cannot be 0. Must be positive and does not equal. So you can put anything you want. Those are the properties. This is a cycle property. Now we can rewrite properties of logarithms. They all come from the properties of exponential functions. You know, product rule, if you multiply two exponents, add the exponents. If you divide, subtract, and so on. So next topic, properties of logarithms. So let's assume a is positive, x sub 1 is positive, x sub 2 is positive, and a does not equal 1. Then here it is. Here is the properties. Logarithm of x sub 1 times x sub 2 base a equals logarithm x sub 1 base a plus logarithm of x sub 2 base a. Logarithm of the quotient base a. It's logarithm x sub 1 base a minus logarithm of x sub 2 base a. Logarithm of x to the power of r base a equals r times logarithm of x base a. Logarithm 1 base a equals 0 because a to the 0 equals 1. Again, a is not 1 and positive. Logarithm of a base a equals 1. Why? Because a to the first power equals 1. Logarithm of 1 over a, 1 over x base a equals negative logarithm x base a, x positive. And we saw the cycle properties. Logarithm a to the power of x base a equals x. So x must be any real number. Number 8, a to the power logarithm x base a equals x. Here's the x must be positive real. And the last formula is a change of base formula. So let's say I have a logarithm b base a. Then it equals logarithm b base c over logarithm a base c. Here a is positive, a does not equal 1, b is positive. On the right hand side, c must be positive, c does not equal 1. Change of base. Now I'm going to prove some of them. Some of them I already proved. Let's prove number 1. Prove. So number 1. Let m sub 1 equals, let's call, let m equals logarithm x sub 1 base a. And m equals logarithm x sub 2 base a. Remember, logarithmic statement means what? Exponential. So it means a to the m equals x sub 1. Over here, a to the n equals x sub 2. Multiply both equations. You get a to the n times a to the n equals x sub 1 times x sub 2. Use properties of exponents. Keep the base, add the exponents. Now move to exponential state. Logarithm of x sub 1 times x sub 2, base a equals m plus n. But what the m stands for? M stands for logarithm x sub 1 base a. What the n stands for? Logarithm x sub 2 base a. There we just proved number 1. So how the number 2 comes out? So again, properties, you should always read from right to left, left to right. Logarithm of the product, sum of the logarithms. Logarithm of the sum with the same base is a product. So let's prove the following. Number 2. Let me move to the left. Let me move this part to the left. Then I get logarithm x sub 1 over x sub 2 base a plus logarithm x sub 2 base a. Hey, we're adding two logarithms with the same base. It's logarithm of the product. X sub 1 over x sub 2 times x sub 2. X sub 2 cancels, you get logarithm of x sub 1 base a. Now move this to the right, you get exactly what we're supposed to prove. Now from here, logarithm of x sub 1 over x sub 2 base a equals logarithm x sub 1 base a. Move it to the right, minus logarithm x sub 2 base a. So we just proved that. Number 3, very similar. Let's prove it. Here's the number 3. Logarithm x to the r jumps in front of it. So let m equals logarithm x base a. Then it means a to the m equals x. Let's raise both sides to power r. Then we get a to the power m times r equals x to the r. Now let's move to logarithm statement. Logarithm x to the power of r base a equals r times n. So r, what the m stands for? Logarithm x base a. We just proved that. Logarithm x to the power of r jumps in front, we get log x base a. How to prove this one? Number 6. I can use number 2, quotient. By the way, this one is proved, 4 and 5. It's a quotient rule. It's a logarithm 1 base a minus logarithm x base a. But logarithm 1 base a equals 0. So this one is 0. So you get negative logarithm x base a. So we just prove that. And those two already proven. I have to prove number 9, change of base form. I'm going to prove it using number 8. So in order to prove 9, I'm going to multiply by the log A base. So let's see, log A base times log of B base A. I have to prove that equals logarithm B base. So I have to prove this product of two logarithms equal. Suppose I don't know if it's equal. Let's take a number C and raise to the power of this number and this. So it's a logarithm ABC times logarithm BBC. C raised to the power logarithm B base. So logarithm, let's use the property. See this? I told you how to memorize logarithm properties. C goes into box 1, so this is C and C, and A goes into box 2, so here we get C to the power logarithm A base C, then raised to the power logarithm B base C. So what is it? C goes here, box 1. A goes box 2, the answer is box 2, so inside of the bracket, box 2 is a logarithm B base A. Now, use the same formula. A goes into box 1 and B goes into box 2 and C is box 2, B. The same thing on the right hand side, C raised to the power log B base C. C goes into box 1, B goes in box 2, the answer is box 2. Hey, they equal each other. So they equal each other all the way up. Let's move up. Let's move up all the way in the chain. So now we get from here this one equals and this one. And why they equal each other? Why the exponents must be equal each other? Because C does not equal 1. In the change of base formula, if you look at this, the requirement is C does not equal 1, C positive. Okay? So this is crucial. From here, we get this one because of the C does not equal 1 positive. So from here, we get this one. So we just proved that. So it's called change of base formula. So now we can bring all the logarithms to one base. What is it? So those called natural and common logarithms. Let's talk natural and common logarithms. So here is the definitions. Logarithm x base 10 is called common logarithm, log x. If you put log x without anything, this means common logarithm. In Europe, they use LGX. It means base 10. It's called common logarithm. It's built in your calculator. Your calculator has base 10 and also base e. Here is the next one. Logarithm x base e. It's called natural logarithm. It's called natural logarithm. This number is e. is defined as a limit 1 plus 1 over n to the power of n goes to infinity. If you calculate, it's approximately equals 2.781828182845, and so on. It's irrational number. So why they use E? Because it was named after Leonhard Euler, who introduced this number. Famous Swiss, German, and Russian mathematician. So now we can calculate any logarithms moving to the base 10 or base E. Here it is. Let's say logarithm 7 base 5. So you take log of 7 over log of 5. Let me tell you what it is. I'll use a calculator. Here it is, log of 7 divided. I have a log key here. Here it is, log key. Log 5. So it's approximately 1.20906, and there are more. So that means 5 raised to this power gives you approximately 7. It's irrational number. Or you can use base E, it doesn't matter because we just proved no matter which base you go, you get the same answer. Let's do another one. ln 195. Hey, here it is, ln. It's built in your ln 195. 5.273. I'm gonna round. Let's get logarithm 17. Logarithm 17. 1.230. So you can get those using your calculator. Now, last thing I want to show you is the graphs, okay? So I talked about the graphs. Let me show how they look like. Here's the graph of y equals 2 to the power of x. As you see, so it looks like it's crossing, but it is not, okay, if you approach this. So it goes from positive on the infinity, it's still positive, goes and it increases. So it's increasing function. Here's the other one, when the base 1/2, it's decreasing function. They both approaches x-axis, which is y equals 0. It's horizontal line. Okay. So let me show the counterparts. This is logarithm. This is y equals 2 to the x. This is logarithm x base 2. See, they're symmetrical, as we proved in the theory of inverse function. The graphs of original and inverse, they're symmetrical about y equals x. Same thing true about this with the base between 0 and 1. You see this? X equals 0 is a vertical asymptote here. So this is the brown line is y equals 1/2 to the x. And blue line is logarithm x base 1/2. You see, this is decreasing. They both decreasing function on its state domain, and they're symmetrical. One is the mirror image of the other. So this is how we can see the graphs of the function and inverse symmetrical about the line y equals x. And I can show for fun another one. Here it is, parabola. It is 1-to-1 on its domain. What is the graph of its inverse? Here it is. They're symmetrical. If you put mirror on the y equals x, they're mirror images of each other.